Okay. Yesterday we were talking about the sine inverse, cosine inverse, tangent inverse, and I mentioned that we're going to talk about this in more detail later when we get into like actually graphing these functions, which we will. But I think it does warrant some discussion right now in regards to where this chart is coming from and where this information that they're giving us, what it means to us, and how we can use it, or how we can maybe even learn it without having to memorize it, right? Okay. So I want to kind of talk about the actual sine and cosine curves that kind of take us back to college algebra days, okay, and our understanding of functions. If I take the sine function, sine of x, okay, now I have to use x. You can use any variable you want to, so all this stuff in the PowerPoint is presented in regards to theta. I guess it does give me x's and y's here, but you can use x, you can use theta, whatever. But if I'm going to use the graphs, obviously we need our x-axis and those values. So we get that function. That is the sine function. Okay, it's a periodic function. What we mean by that is that it repeats itself over and over again forever. Okay, you can go out as far as you want on the x-axis, and that thing is going to keep doing the same exact thing over and over again. And the question is this thing, obviously it's being called a function here, but why is it a function? It passes the what? Passes the vertical line test. Maybe. There we go. Pass the vertical line test. We can move that line through there anytime we want to, and it only intersects one time, right? But is it one-to-one? Meaning, does it pass that test? No. Okay, and when it fails that test, it tells us we don't have an inverse. Okay, but we do have an inverse. We know we have an inverse. We've talked about it. We've used it on our calculator before. So here's how we make this thing have an inverse. Is that we look at this curve and say, okay, it's going to repeat itself over and over again. And that repetition maybe allows us to kind of shorten this curve and only look at a certain section of it. Okay, and I want to look at a section that is doing just kind of one behavior. And what I mean by that is it's only increasing or it's only decreasing. Because if it's doing both, if it's increasing and then it decreases, okay, think about this. Let me trace here. If it's increasing and then starts decreasing, doesn't that provide a situation where we fail the horizontal line test? Okay. Or if we're decreasing and then start increasing, we fail the horizontal line test, right? So I want to look at a set of x values that this thing is only increasing on, and I probably want to choose them close to 0, 0. It just makes it easier if we're looking around the origin here. So I find that minimum, and I find that maximum. And the curve between those two things, would you agree that is only increasing from left to right? Okay. We refer to that as being monotonic, okay? Meaning it's doing one thing all the time, okay? So we got to figure out, okay, what were the input values? What are the x values that this occurs in? And you'll know this stuff, and we'll talk about it in greater detail later on, towards chapter 6. But this x value of that minimum right there, okay, that x value is pi over 2, negative pi over 2. And that x value that goes with that maximum is positive pi over 2, okay? Because if I type in sine of pi divided by 2, you see that gives me 1 back, right? So sine of pi over 2 is giving me that y value of 1 back. Negative pi over 2 gives me a y value of negative 1 back. So what I really want to do here is look at the sine function, but I want to look at it between negative pi over 2 and pi over 2. And there is my restricted pi function, not restricted sine function, between negative pi over 2 and pi over 2. Okay? That's the domain, right? Does that make sense? Those are the x values. Okay? The range, what is your range values here? What's your smallest y value you're getting back? All right, and what's the largest y value you get back? Positive. So -1 to +1 is my range. Now my input values right here, they're in terms of radians, right? Now on this this x-axis here, okay, that value of -1.57 is about right there, right? Okay. The value of 1.57 is about right there. Okay. But it does usually make a little bit more sense to graphically look at this thing maybe this way. So our x-axis is written in terms of pi. So when I do that, okay, instead of this being 1.57, it's now written as -pi/2, right? So we're seeing that our input values that come off the x-axis, the input values are an angle measurement, and the output values are a ratio of side lengths. Is that okay with everybody? Okay. So what this means to me then is if I've got this point right here, if I calculate sine pi/6, the y value that it gives back should be 1/2, right? And that's what the sine function does on your calculator. If you type in sine pi/6 in radian mode, it will spit back this 1/2, right? So that is an ordered pair of pi/6, 1/2. Is that doable? So how does that relate? If that thing is the sine function and it's now 1-to-1, it should have an inverse, right? If that point is on the sine function, what do the x and y's do in the inverse? They flip-flop, right? Okay. So I should have a y value, or sorry, an x value of 1/2 and a y value of pi/6 in the inverse function. So let me graph that for you real quick. Okay. Now the idea here is when we do this, it makes sense for us because these points, okay, any point on here, let's put this point right there. Point C, obviously it's written in decimal version here, but that point right now is pi/6, 1/2. Okay. Well, when I find its inverse, the pi/6 becomes the y-axis, right? So you see how I just transformed? I highlight the radian measurements on the y-axis. Does that make sense? Okay. But 1 is still on there, 2 is still on there, 3 is still on there. All your real numbers are still on here. It's just that we're highlighting the convenient versions right now in terms of multiples of pi/6. Everybody all right with that? And instead of highlighting the multiples of pi/6 on the x-axis, now we go back to highlighting just the maybe rational numbers. Okay. So now when I look at this curve, and then I want to take the inverse. Remember, the inverse is a reflection of this thing over the line y equals x, right? Okay. So I'm going to actually I have to type in arc sine for this. Type in arc sine. Okay. You see it puts it in both graphs right now, but you see that that's not the same thing as the purple one, right? Okay. So the orange one here is the reflection across the line y equals x, but I want it only in that block there. So let's kind of condense this stuff a little bit. Zoom out maybe. So now, any point, this point C was at pi/6, 1/2. Then I should be able to, on this curve right here, on this orange curve, I should be able to locate the point 1/2, pi/6, shouldn't I? And you see that it shows up on that curve. Does that make sense? Okay. So when looking at the original sine function, okay, you have a domain that goes from -pi/2 to +pi/2 in a range that goes from -1 to 1 when I restrict the domain. Does that make sense? Okay. Generally speaking, the domain for the sine function, with no restrictions, is all real numbers. We had to restrict it so that we get an inverse. So now if that's my domain and my range for that restricted curve, over here, when I find the domain in the range of the arc sine, so the arc sine over here, or the sine inverse, how you want to phrase it, the domain is now between what numbers? -1 and 1. And the range is between what numbers? Yeah, negative pi over 2 and positive pi over 2. And what happened there? Because they're inverses, the x's become the y's, and the y's have become the x's, right? Is that all right, everybody? All right. Over here, remember yesterday we talked, whenever I use the sine function, I'm typing in an angle as my argument, and it's giving back a ratio of those side lengths, okay? In this case, sine, so it'd be opposite and hypotenuse. So that's your input value, or graphically right now, that's your x value, and that would be your y value. When I deal with the arc sine over here, your input is the ratio, and the output is the angle, okay? In a case, in this curve, that's still an x and that's still a y. But does that kind of make sense, everybody? All right, that's where all the information, all the numbers on our calculator are going to kind of come from. What I want you to understand is that when you take your calculator and hit sine inverse, your output numbers that you get are only going to be numbers between negative 90, if we're in degrees. I think talking using degrees right now maybe is a little bit easier. My output values are only going to be numbers like negative 90 to positive 90. Okay? I will never be able to get an output value of like 210 or 130 or 150, 180. Does that make sense? Okay? But there will be times where we know that, the sine of, let's say, 1/2, about this way, sine of 1/2, if I have a ratio of 1/2, what is the angle that goes with that for the sine in the first quadrant? 30 degrees. Okay? Meaning then that over here, if I go sine inverse of 1/2, it should spit back 30, right? We'll do that. Take my calculator. I'm going to make sure I'm in the right mode, degrees. So I'm going to go second sine, 0.5, spit back my 30 degrees, right? Okay. But don't we also know, so that would be a picture that kind of looks like this, and I know I've got a lot of stuff up here, and it's getting cluttered, but that would look kind of like that, where that's 1 and that's 2. That would be your 30 degrees, right? Could I also have a picture that maybe looks like this? Would this y value still be 1, positive 1? And could this still be 2 here? Okay. Would that angle be 30? Or would that angle be 30? The red angle is 30, right? Okay. So what is this black angle? 150, right? Does that make sense, everybody? Okay. So the sine, what I'm getting at here is the sine of 150 will also spit back 1/2 to you. Okay, type that in, sine of 150 spits back 1/2, right? But if I type sine inverse of 0.5, it's going to give me that 30 back. I can't get this 150 back, right? Because we talked about that when you use the arc sine, when you use the sine inverse, what are the only kinds of numbers that you're going to get back? Between negative 90 and positive 90, right? Well, 150 is outside of that, right? Okay? So, there will be situations, there will be times when the question says, we want you to do the work and get the 150-degree answer. Okay? But they'll tell you that, the sine inverse of 1/2, when you evaluate that, it'll tell you that the theta that you're dealing with is in the second quadrant. So I use my calculator, I evaluate sine inverse of 1/2, gives me 30. I now know it should be in the second quadrant. So now I'm thinking about that picture there, and it's actually 150 degrees I'm dealing with. Does that make sense? The calculator won't spit back to 150. It can't. Okay, because how it's referencing the the one-to-one relationship between the sine function and the sine inverse function. Okay. So I know that's a lot of stuff, and again, we're going to talk about that in a lot more detail later on. And you'll obviously kind of manipulating it from here until then will provide you a lot more understanding later on when we talk about it again. But I don't feel comfortable giving you, because I've been in your seats when this has happened as a student, and give you this information, this chart, and just tell you to learn it, memorize it, and you have absolutely no idea where it came from. You're using your calculator and it's coming up with these magical numbers and you don't know why. Maybe when you see those numbers now on your calculator, you can kind of have a grasp of what they mean, where they come from, why they are what they are, that kind of thing. Now the cosine function is a similar thing. Okay, so let me just look at cosine of x over here. So there's your cosine function. Looks a lot like sine, right? Repeating itself. If I put sine in with that, okay, so the gray one here, zoom in, the gray one is the sine, and the purple one is the cosine. But you see that they're very similar to one another, right? And they're actually just a horizontal translation of 90 degrees of one another. Okay, and we'll talk about that later on. But they're very similar, but they do have different intervals in which we need to restrict the domain to talk about them being one-to-one. Okay, because again, the cosine function will not be one-to-one in its entirety, right? So what we do is we start with this point here, and we go through the same idea, and we want to make sure that we work our way through so that this thing is always, we choose a domain to where this thing is always doing one behavior, always decreasing in this case. And if I do that, you see if I move C beyond, it would start to increase, right? So the domain that I need to restrict for cosine is between 0 and pi. So that's where they're saying here, essentially how this range shows up here for the sine or the cosine inverse. Okay, so we do that. So let me write that in here, cosine, and I'm going to look at it between 0 is less than x is less than pi. So it gives me that thing there. And you guys know that maybe doing this a little bit differently than I did the last one with the sine function. These should be reflections of one another across the line y equals x, right? If this thing has an inverse, y equals x. This curve has an inverse because it is one-to-one now. We should be able to take it and reflect it across that line right there, right? And when we do that, reflecting across that line, change the color here. Okay, reflecting across that line, that red curve is developed, right? And reflecting across that line is just the, if you remember back to college algebra, it's just the switching of the x's and y's. Make the x becomes y's and the y's become x's of that purple curve. But now when I look at this thing, let's actually get this one to go away. Let's get that to this. Oh, I'm going to hide it, I guess. That curve right there is the cosine inverse. Okay. Now the cosine inverse is going to have x values that we input here between. Let's actually get back to, because the inputs are going to be ratios. So let's get back to the x-axis being labeled with our integers. And we see that if I put my grid lines in here, what is your first x value that you're allowed to use? -1. What's the last x value that you're allowed to use? 1. And that's where we're seeing in this here that the domain for the cosine inverse is -1 to +1. The range of this curve, I'm not going to change the y-axis, but I think you guys can view this. the first y value you'd come across would be what? 0, right? And the last y value is a smidge above 3. Well, how big would this? What do you think a smidge above 3 would be for this curve? Pi. And that is where that pi is coming up. Now, obviously, we've talked about the smudges on here. Those are pi's. I don't know what's going on there. But I wanted you guys to see that that's where these functions, domain and range, come from. That's where that information is developed from. The tangent is simply the sine divided by the cosine, right? Sine divided by the cosine. So let's kind of maybe investigate that a little bit. The sine function looks like that. The cosine function looks like that, right? So if I take the sine divided by the cosine, what that means is no matter where I choose an x value. Okay, let's do it this way. We got a line. All right, so these 2 points, C and D, are the y values from sine and cosine, right? Okay, so if I take this value, the y value that goes with D, and take the y value that goes with C, and I divide those, it's going to give me another value, right? Well, that quotient is exactly the same thing as tangent at that x. Does that make sense? And right now I've got x at being -1. Okay. Let's go over here. Let's say that x is at. I'm going to move this point. Maybe use that one. I'll move both of them. Okay, hold on. Maybe that's the line I'm looking at. Okay, so x is whatever that value there is. You're seeing, hopefully, that C and D have the y values are the same, right? 0.7. Okay, and they're actually 0.707. They're actually radical 3 over 2, I believe there. But when I divide those by themselves, what do I get? I get 1, don't I? So at this x value, when I graph my tangent function, it should have a y value of 1. Because it's taking the y values off of these two curves and just finding the quotient between them. Does that make sense, everybody? So if I take the sine function, which is f of x, so those y values, and divide them by the y values from g of x, I end up with those values. Okay? So those values, those are your tangent curves. Okay? And even if I just use tangent of x and type that in, you see it to go over the top of it, right? Okay? But we've got some issues here, because if I look back to here and I do that division thing, okay? Let's say that my line that I'm using to divide is maybe that line right there, okay? What would be the y value of point B there? 0. And the y value up here would be 1, right, on that curve? Well, what's 1 divided by 0? Can't do it. So graphically, college algebra says if I can't do that division, it's undefined. What kind of line should that be right there? Okay, that's an asymptote. Okay, and that asymptote actually occurs at x equals pi over 2. Okay, you see here that we're taking that y value there of 1, that y value of 0, and dividing them, and that's undefined. So these curves never get there. Okay, so what that tells us, what is nice about that, is because this function as well, by itself, the entire tangent function is not 1-to-1, right? Put a horizontal line through there, and it's going to fail it, right? So what we do is we restrict our domain. Just the tangent function is nice to restrict the domain between two asymptotes. And you have an asymptote at negative pi over 2 and one at positive pi over 2. And it gives me that thing. Okay, and when I reflect that thing over the line y equals x, it gives me that thing. Okay, so that is my inverse tangent function. Now here, look at the domain. What are all the x values you can plug in for your inverse tangent? What are the x values that are being shown up there? All of them, right? All real numbers. Okay, and that's because this thing had y values that were all real numbers, right? Okay, the end behavior says we go to negative infinity, positive infinity. So when I flip those in the inverse and they become the input values of the inverse, it means the input values can be anything they want to be. But the output values now, okay, I'll never get a output value that is greater than pi over 2. I'll never get an output value that goes above that line, right? And I'll never get an output value that goes below that line. Okay, so my inputs are all real numbers, but my range now for the tangent inverse is negative pi over 2 to pi over 2. Okay. Now the key thing, the reason I spent a lot of time talking about this, okay, I spent maybe collectively in the last 2 days about 35 to 40 minutes talking about this, is because of how much we're going to use these things. Okay, and I think if you understand where they come from, why they are what they are, it makes it easier to deal with. You get stuck some point, not sure what you're doing, maybe you can rely on this information and it can get you unstuck. Okay, or allows you to maybe use some technology to navigate your way through a problem to get to an answer. Okay. Yesterday we did some of these examples here, find the exact values of those things. I think we maybe closed class with tangent inverse of 1. Did we do that one? You guys have that in your notes? Okay, so did we do cosine inverse of negative 1/2? We didn't do that one either? Did we do this one? We didn't do any of these? Fantastic. First period we did some of these. Well, I know your second period, Jackson. All right. Obviously, you can take your calculator, right? You can take your calculator and you can find the exact value. You can go sine inverse radical 302, make sure you're in whatever mode that you want to be in. Okay. Right now, probably degrees would be more kind of a visual thing for us to see what the answer is, because if it's in radians, it's not going to put the pi in there for us. We should get 60 degrees back here, and if we were in radian mode, it would get back an ugly decimal. Okay, so let's put it in degrees so we get something nice back. So obviously, technology-wise, this is pretty easy. I type in sine inverse, so second sine, and then root 3 divided by 2, and I get my 60 back, right? Okay. If I were to be in, this is the reason I want to be in degrees, if I was in radians, it would have given that number back, and you don't maybe know if that's a really nice number, right? Okay. Or a really nice angle measurement. Is that okay with everybody? Is that pretty easy on your calculator? All right, let's talk about what it actually means to us in the coordinate plane. It means the sine inverse, okay? That means whenever we're doing the inverse, sine inverse, arc, or even if they use the word arc sine or tan inverse, arc tan, cosine inverse, or arc cosine, this here is a ratio. You're getting back an angle, right? Okay. So your ratio right now, and the sine is going to tell you the parts that make up the ratio. They're telling you your opposite side right now divided by your hypotenuse, right? So my opposite side is root 3. My hypotenuse is 2, correct? Okay. So let's just deal with this in the first quadrant. Because the sine inverse, remember the sine inverse going back up to this blue chart, sine inverse is only going to give output values, range values, between negative pi over 2 and pi over 2, right? Okay, so we're looking at essentially just angles in those two quadrants right there. Okay, so I'm going to deal, because of the nature of those numbers, I know I should be in the first quadrant because radical 3 is positive, right? And the hypotenuse is positive. The hypotenuse always needs to be positive. So I got to be in the first quadrant. I know that's 2. The opposite side is root 3, right? How could I know if I should be in the fourth quadrant? Why don't they put a negative there, and that will tell me my y value has to be negative root 3? Is that okay with everyone? Okay. You can do now a little bit of work and find out with Pythagorean theorem that that is 1. And now the hope is that we've dealt with this enough that we realize that any multiple of that triangle, so 2n, 1n, n radical 3, that provides the template for a 30, 60, 90 triangle, right? And across from the larger side here is your larger angle. So that's the theta that our calculator just spit back to us. Is that all right? Now here's my issue, and this is going to be the issue that you also find later as well. We just found theta. So the question might say, find the exact value of theta, which we did. They might give you, say, extra work or extra information that says, but theta is in quadrant 2. Think about the sine inverse. The way we have developed it, the sine inverse is only going to give you angles that are between negative 90 and positive 90. Quadrant 2 has got angles that are between 90 and 180, don't they? So will the calculator ever give me that quadrant 2 angle back? No. Okay. So here's where we got to do a little bit of work. We got to use some of our logic, because we know that if that's a root 3 and it's positive, there's also a root 3 over here that would be positive, right? My hypotenuse is still positive 2 there, correct? Now my not cosine, but my adjacent side here, that would be now a negative 1, right? Still got a right triangle. What could you tell me about those two right triangles, the black one and the blue one? What do you know about all three sides compared to all three sides? They're congruent, right? You got side, side, side there, congruent triangles. So what does this angle here have to be? 60. Okay, so we're able to kind of cut and paste that triangle over here, right? But the question is always, when they ask an angle of theta, the question is that they're always asking for an angle from standard position. So we're actually looking for that angle there, that purple angle. So how big would that purple angle be? 120, right? Does that make sense to everybody? Okay. So right now we just found out, okay, that with our calculator, sine inverse of root 3 over 2 is 60 degrees, right? Meaning then that the sine of 60 should be root 3 over 2, correct? Does that make sense? Okay. Our calculator, get it out, and we type in, I'll just type in root 3 over 2 real quick to see what that gives me. Should be the 0.707 number, right? Oh, 0.866, sorry. So every time I see that, I'm thinking radical 3 over 2, right? If I type in sine of 60, it gives me that number back, right? Now the sine inverse of that number is going to give what back? It's going to give the 60 back, right? No matter how many times I type in sine inverse of root 3 over 2, it's going to give me 60 back every single time, right? This is how it's recalling that set of x and y values from the inverse function. But what I want you guys to understand is that even though sine of 60 gave me this number back, sine of this angle here should give the same thing back. So sine of 120 gives me back the same 0.866, right? So what I want you guys to understand, and I think maybe it makes sense to show it down here. The sine of 60 is equal to root 3 over 2. The sine of 120 is equal to root 3 over 2. However, I will never, with my calculator, be able to type in sine inverse of root 3 over 2. Will it ever spit back 120? No. Okay? Because if it does, we now have two different y values to go with the same x value, and it's no longer a function. Does that make sense? It fails the vertical line test. So it will never give back that 120. But there will be situations where we want that 120. And they're going to tell us additional directions to say, hey, it's in the second quadrant, it's in the third quadrant, whatever. Is that doable? Okay. Now, obviously, here they don't say it. They don't tell you that you have other possibilities. So the assumption is we're going to just use the smallest angle that we could deal with. Okay. So here, doing cosine inverse of negative 1/2. So that ratio, negative 1 over 2, this is the opposite side divided by the hypotenuse, right? Now the cosine inverse, if we go back to the blue curve or the blue chart, is going to give you angles in those two quadrants. Okay, those are the only output values you can get back from the cosine inverse, from 0 to pi. So which one of these quadrants, quadrant 1 or quadrant 2, are we going to be able to use a negative number in? Quadrant 2, right? I've got to have an angle over here so that the adjacent side is negative, right? Any triangle I put in the first quadrant is going to have all positive values. So I need to be over here in the second quadrant. So the adjacent side is negative 1. This is 2. Okay. Now the hopes are we can use the Pythagorean theorem and find out that this is root 3. Well, across from the radical 3 side is always a 60-degree angle. Okay. So here when I say cosine inverse of negative 1/2, we're talking about that angle right there. How big is that angle of theta right there? If this triangle's got 60, that theta is... Is there somebody talking out in the hallway? That was video? Somebody's deaf. All right, so we should get 120. Somebody said 120, right? Okay. So we got 180 there. We know that that's 60. Coming back a little bit, then will be 120. So that means then, when I take my calculator and I type in cosine inverse of negative 0.5, I should get 120 back. Okay. Now here's the thing. Isn't cosine negative in this quadrant and in this quadrant? Okay. So there's a reflection. There's another triangle down here. A congruent triangle. It would allow me to find maybe that angle right there. Okay. So hopefully you can see that 180 plus 60 degrees would be 240, right? So the cosine of 240, also gives me a ratio of negative 1/2. Okay. However, the ratio of negative 1/2 on my calculator will never give me back the angle of 240. Does that make sense? Okay. That is something that I'm spending a little bit more time talking about this year with you guys, because in the past, I don't know if I took the assumption that people understood that or it made sense, and it became kind of problematic as we moved through the rest of the course. Do this tangent one real quick just to get it on our notes, but tangent inverse 1/1. Tangent is opposite divided by adjacent, right? Okay, so here we've got an issue that either the opposite and the adjacent are both positive, or the opposite and the adjacent are both negative, right? Okay, but tangent inverse, if they were both negative, it'd be third quadrant information, right? Okay, well, go back up to your tangent inverse. Your tangent inverse output values are never in the third quadrant, right? They're in the first and fourth quadrant. Okay, so when they give me this information, we're dealing in the first quadrant. I know my opposite and adjacent. To get one, they have to be the same number, right? It could be 3 and 3, it could be 12 and 12, it could be pi and pi, it could be root 5 and root 5, or 1 and 1, right? And that would be root 2. And that then ends up being a 45-degree angle. Okay. We know it's a right triangle, right? It's isosceles. A right isosceles triangle is always a 45-degree angle here. So that means that if I type in tan inverse of 1 on my calculator, it's going to spit back 45. Or if I type in tangent of 45, what's it going to spit back? 1. What other number can I put in there that's going to spit back 1? Good, 225. Okay? Because down here, we got that congruent triangle, or that's -1 and that's -1. That quotient is still +1, right? And the angle then there with the x-axis and that terminal side, that would be my 45-degree angle. We got some vertical angles here. All that stuff from geometry is consistent. And then 180 plus that 45 would give me 225. Just as you pack up and keep talking a little bit, you're going to see questions that ask you to do this. Find the approximate values of the given expressions. When you see numbers like 1, 1/2, radical 3 or 2, radical 2 or 2, those types of numbers, you should be able to draw a picture, get a good idea, use a special right triangle. If they're ugly numbers like 0.71, you got to use your calculator. Okay? Tan inverse of 2, nobody's going to memorize that. Maybe right now, so you got to use your calculator. Okay? And they're just asking you then for the approximate value in regards to an angle that spits back. Is that all right? You guys can do part B. These, and I'll get them on video tomorrow with you. But these are things that I think we should be able to do already from Algebra 1, 2, and Geometry. Just drawing these pictures. It's okay, if I want to find theta, don't I just have to use opposite over adjacent? So sine. Or sorry, opposite over hypotenuse. So I'd say sine of theta is equal to 1 over 5. Would you guys agree with that? Yes. And now to get that theta out, this is the algebra we do. To get that theta out, we take the sine inverse of this side. And we take the sine inverse of that side, right? And that's a parallel with, like if I had x squared, once you take the inverse of that side, you square root that side to get x out, right? So I take the inverse of this side to get theta out, and it leaves me sine inverse of 1/2. Hopefully not 1/2, 1/5. We grab our calculator then, we type in sine inverse of 1/5, and it gives me that angle, right? Once I have that angle, can I subtract it from 90 to get that one? 90 minus theta. And can we use Pythagoras to find that side there? Okay. That side's going to be what? 50 squared minus 10 squared. And then underneath the square root. So that's solving the triangle. Let's find all the parts using the knowledge from Algebra 1. And this is kind of what's, I think, backwards sometimes about mathematics. You've been using the sine inverse and sine buttons since like the 7th grade, right? And now you're juniors and seniors and finding out where they actually come from, right? So I think it's kind of backwards the way we do some stuff, but hopefully it makes what you already know maybe a little bit more concrete. So we'll continue with this tomorrow, pick it up, finish it up. I will open up the 5-4 today. We'll be able to start that and get a big chunk of that done. So that will open at some point.